I'm so glad that I'm here today. It's my first time in Poland, and I gotta say I have a lot of friends in Poland, but I've never been here, so I'm quite glad. So today I'm here to talk about finite states and how we can use them in the context of UI development, or specifically talking JavaScript development on the front-end side. So before we get started, let me give you an introduction about me. My name is Farzad. I'm originally Iranian, but I live in Finland and work as a software engineer in Epic Games. Do you know Epic Games?
Yes.
Cool, because I didn't know before I joined them. So I'm not going to do any dance of Fortnite on this stage. I haven't played Fortnite myself, but if you have any questions, please come over after the talk. I won't be able to answer them. So before becoming a software engineer, I was studying aerospace engineering back in college. Side by side astrophysics too. I was always a nerd back in high school, reading mathematics and physics, backing the whole of the library by myself, no girlfriend. But then I went to college and I found out that my passion is aerospace engineering. I started programming in the context of scientific programming with Python, MATLAB, Fortran, Pascal, these languages. But then at the end of but like in the middle of the last semester of the college, I found out that, oh my God, this is not how I'm gonna end up with my life. I'm not gonna be like living in the lab for the rest of my life. So I dropped out of college. And I started self-teaching myself software development 7 years ago, and I learned from the web, and I'm here today to teach the web again. So today we're gonna talk about what is implicit state, what is explicit state, how they differ from each other, how we can say that if the state is finite or infinite, and then we will move over to the next part of the talk and we'll talk about the logic, how we can model it, visualize it, and how we can decouple it in a way that instead of getting into the implementation detail, we'd be able to model the logic of some part of our UI. Also, I can show you how you can port this logic per se to different platforms. For example, if you're working with web and mobile at the same time, you want to have like isomorphic JavaScript, universal JavaScript on different platforms, you can use this approach to port the logic to different platforms. You're all JavaScript developers here, right? That's not a lot of nodding, but cool. Do you use any state management tool? Redux, hooks in React, context, MobX, RxJS. Some people think Rx is a state management tool, but it's not. So let's see what's the problem with these tools. Go over how we can think about them, how we use them together, and see what's the problem and what are the solutions. So with the modern frameworks on the front end side, we see a premise as a tagline as the frameworks called the UI is a function of the state. We see that they promise us in a way that we can declare and define what we want to render as components, and then they will take care of the actual implementation down to the DOM level for us. When you're working with React or Vue components or even Angular components, not AngularJS, you're dealing with some sort of DSL on top of something that the library is giving you. They abstract away all the complexity and you're dealing with JSX or HTML or other sort of syntax. And one part of this statement here is the state, and that's what we want to focus on today. So in JavaScript, we do one thing in different ways. For example, if you're using domain-specific solutions such as React hooks or React props and state model, you can update the title in a way that it uses setState. If you're using MobX, you can use decorators or other fancy features like proxies or mutations. You can use Vuex and Vue, and you can use like normal hooks in React. There are different ways, but they're basically doing the same thing. But in my opinion, these state management tools that we use these days, they're not managing the state, they're containing the state. Why? Because they're dealing with the state architecture. They're giving you a way to deal with the state in a way that you say, oh, I'm following the flux architecture. It's a unidirectional architecture, or I'm following a push-based architecture or pull-based. I subscribe to the store, and whenever there's a change, the store will let me know, and I re-render. Or I'll just pull for the changes of the store, and then whenever I see a change, I re-render. These are like different mechanics behind how the architecture of a state management can be handled. And basically, how React handles these down to the component level, or how MobX handles this, or how Redux handles it, they're different. These state containment tools also give you a way to store the state. They give you a way to be able to store the state whether in a single source of truth, like Redux, or distributed down to different sources throughout your whole application, like MobX. They also give you a way to update the state. They tell you if the state is mutable, you have to have mutations, or they're immutable, so you have to have immutable operations. Instead of using splice on arrays, you're supposed to use a slice from now on. Or they're observables, you have to subscribe to them in order to be notified by the changes. So you see, these are the purposes of using the state management tools these days, but they don't really manage the state, because managing the state means modeling the state. They're not modeling just because they don't want to handle that part. They're not tackling that problem. So what we're going to deal with today is that this is the normal flow of the state management tool right now in JavaScript. They give you a mechanic, you have to dispatch actions, and your UI will be notified. But what we're going to add today is a modeling layer in between, so that instead of your view, talking to the whole state management tool, dispatching actions directly, you talk to the modeling layer, and the modeling layer would be the brain. You send event to it, you say that, okay, I'm in this state, I want this event to happen, and the modeling layer will calculate something, and then dispatch actions to the state management tool. So you add a brain in between. Before getting to the actual implementation and talking about the library or other things, let's have a really quick flashback to GUI history. The research and development of current approaches to GUI development that we see in almost 2020 started back from 1972 by Alan Kay and his team. So basically they were assigned to a project that they were supposed to do research and development based on the Smalltalk language to be able to build a portable laptop or notebook or computer or whatever you want to call it for kids, so that they could interact with it. It would be as easy and interactive for a kid to be able to interact with it and learn something. So they were doing research and development, they were using Smalltalk, and surprisingly they came up with a very good model that's called the event-driven architecture or event-based model. It means that they said since GUI is a sort of entity, UI is an entity that the external user who's using this UI is sending different external events to it, it makes sense to be able to use an event-driven approach to develop this UI. And since 1972, 48 years, we are still following the same paradigm, which is called event action. We are still using add event listener in DOM, right? It's 2020, 48 years after that, but we're still following the same thing. But this event action paradigm, despite how it scales well and it fixes most of the problems, there are some problematic things that can happen while following this. So let's indicate what the actual problem is. Let's see a video. Okay, so what happened in this video was that there was a severe security bug in FaceTime. So you could call someone, and before that person behind the call accepts or rejects the call, you could bring up a UI from the bottom by swiping, add another person, and by this adding gesture, you could eavesdrop the person that hasn't started the call yet. So I could call you, you didn't know I'm calling you, you haven't accepted or rejected it. I could do something, there was a bug, and I could listen to your phone. That was a severe security bug in FaceTime. We will see the reason behind it later. Another problem by following event action paradigm in the history was the Microsoft Calculator application, the basic calculator application that was shipped by Microsoft Windows. So basically there was a professor called Ian Horrocks who wrote a very good book called Constructing User Interfaces with State Charts in 1999. In this book he describes how in 10 minutes he messed around with his calculator, and by pressing the clear button and the minus button, he was able to produce several logical runtime errors. And there were reasons behind that. The FaceTime bug and the bug that happened here was simply because the developer of these applications were assuming that the events and the side effects in UI map to each other one-to-one linearly. Basically, it means whenever I click on the minus button, start this mathematical sequence. But the problem is, this minus button could have done two different things. If it was used in a mathematical sequence, it should have subtracted those consecutive numbers But if you were using this minus button before the first number in the sequence, it should have negated. So if you use minus then 2, then plus 2 will convert to minus 2. The same way, in reverse. So the same button could do multiple things. It means that when I press on single button, one event, two things could happen based on the context I'm calling this button in. So the problem was the event handler was suddenly needed to be context aware. But the main problem beside that was that these applications were handling the state of the application implicitly. So how we handle implicitly means that we write this sort of code. Have you seen this code? If you work on a product, you've seen hundreds of this in different modules, and you have to like move between these modules and different files, read all these if and else branches, and try to understand what's the logic behind this, and try to understand what's the feature that has been implemented just behind these if and else's. By handling the state of the application implicitly, we not only end up in those box, but also to understand what the code does, you have to understand what event handlers are, mutations, asynchronous stuff, concurrent stuff, all the side effects. You have to understand all line of codes just to understand what's the logic behind it. And that's not feasible in product development. So impossible states are one of the problems that come with handling states implicitly. Let's see a practical example from 2019. Let's strip out the Microsoft calculator bug and stuff like that. Let's see something that is tangible for us. This is the input from the login form at Netflix. You use Netflix, right? If you wanted to use the login form, this is the email input. So basically the email input could have 4 different iterations. It could different in 4 different variations. It could render differently. So once you open the page, the input was empty, and then you start writing something, and suddenly something pops out as an orange text that says, oh, you know what, this is not validated. This is not a valid email. Then you try to clear it, it stays there. It's not the same as the first one, and then you write something here, and then suddenly it's valid. Do not use this, please. This is my personal email. So if I wanted to use a state object in 2019 with all these modern shiny frameworks and try to model this iteration, I would say that I have a state object that has value and there's a valid boolean. So in the first iteration, we could say the input is empty, so there is no value and it's not valid. The second one, there is a value, but it's not still valid. In the third part, you could say the value is gone again, but valid is false. And on the first one, you can say that there is a valid value and valid is true. So the problem here is that there are 2 same state objects that are supposed to render differently. And this is how we handle the states implicitly, by trying to reason based on the state of the application, based on some data structure or an object. And how it handles is that the state is not capable of rendering differently. So we can't have the purpose that we want to render. So what we do is that we add another Boolean flag. We say that now we need to understand whether the input has been validated before or not. So we add another Boolean flag and we say that it's false. Then as soon as you start typing, we try to validate. So this would turn to true, and it will remain true. And basically, based on these 3 variables in the state, you are now capable to render differently. It works, but there is a problem. The problem here is that you're reasoning based on 3 different variations. The variations of the length of the value of the input, the variations of values of valid and is-validated booleans. So when the input is empty, the length is 0, valid and is-validated are false. And same goes on and goes on. So you toggle different properties in the state object and you try to render differently. This works, but the problem is here. So the length of the input can have 2 different cases. It's either 0 or non-zero. The value can either be true or false, and is validated can also be true or false, which means you have 2 raised by the power of 3 cases, which you only wanted them to have 4 renders, so there are 4 renders that you don't handle. And that's called the state of implicit states. It means that the code that you modeled in your state right now, it grew more than it was supposed to. Your state is capable of rendering 8 different variations, but you only wanted to handle 4 of them. So the rest 4 of them are there. They can technically be reproduced down to the rendering time, but you don't use them. So what you do is that you use this implicit state and you end up with problems, but I can show you the solution. But so before getting that, know that by modeling these implicit states, it's a bad modeling, so your code complexity will grow faster than the domain complexity. The domain complexity was that you needed 4 renders, but now the state is capable of rendering 8 different variations. So the complexity of the state is twice the problem complexity itself. And impossible states, with them, you need to now write tests in order to avoid your code to render those 4 impossible ones. So you write tests not only to make sure that the things you want to work, but also make sure that the things you don't want to happen, they don't happen. With impossible states, it's exactly the time that you tell the users you need to restart. Have you ever seen the blue screen of Windows? Have you ever seen a login form that the button is disabled even though all the inputs are valid and the only way to make it work is to refresh the page? That is where the UI is end up in an impossible state. So it's an impossible state. The developer didn't predict that, so they didn't provide a way to recover from that. So the only way is to restart the page. Another problem that happens with implicit state handling is mutual exclusivity. It's a very fancy word, but basically it means 2 properties are mutually exclusive if they're not supposed to happen at the same time. So if you use this input in the form, now you can also model the state of the form too, because of course the UI is not always as simple as just single input, right? I wish it was, but it isn't. So you use it in the form, and now you say, oh, okay, now I need to model the state of the form, so I have submitting to indicate whether the form is being submitted or not, and I need an error object that can be either a string or undefined in order to store the error that comes from the API response. So when the form is editing, you submit is false, but error is undefined. When you're submitting, something gets true, error is still undefined. When the submission fails, now there is an error, but submitting tag goes to true. And when it succeeds, the error is undefined and submitting tag goes to false. Now the problem is, this impossible state happen again. But in this case, these are mutually exclusive, meaning that the form is not supposed to be submitted when it's not validated yet. So form being validated and form being submitted are mutually exclusive. They're not supposed to happen at the same time. But the state that we use makes it technically possible. So there was implicit state handling had 2 problems. There were impossible states, something that you didn't want to generate, but it can be generated technically, and there are mutually exclusive things that are not supposed to happen at the same time, but your state makes them happening at the same time. So you go on and add another Boolean flag, the same input problem that we saw. And it turns out like this, it works, but it's fact. It doesn't make sense. So to avoid these impossible states and mutually exclusive behaviors from happening, we not only test, but down to the runtime, we also need to add guards because we don't want our code to happen. So what we do is that we add guards. We say that, okay, when the input is changing, if it's not validated, set the validated to true. These are the guards that we add in order to avoid going to those impossible states. So that the code could generate eight different variations, but now these will avoid going to those 4 impossible ones. Make sense? But the problem with guards also is that they work fine for most of the cases, but they increase the cyclomatic complexity. Cyclomatic complexity means different ways that your code can end up with. If you add if cases, if you add else, if you add while, for, switch, case, these are the things that branch the code. So if you use if and else, your code is now going to end up in 2 different possibilities. Either this is true or false. These are different branching, so the code it's like a story, it can end differently based on the path that it takes. So when the code complexity increases by if and else and the state you use, the problem is now it's not as predictable and as easy to understand as it was before. You not only can add guards by adding if and else and stuff to your JavaScript logic, but also you can add guards to the rendering, like disabling the submit button. But the problem here is that disabling the submit button in a login form is not the business logic of the product. So of course it tries to prevent the problem, but it's not the actual solution. The solution is that not to write a code that is fragile. So what can be the right solution for this? we need something that can let us think about the states explicitly. Instead of having a state object and reasoning based on some primitive data types, we need to think about the states explicitly. And for that, we need to develop a skill to be able to see the finite states of the application. So what are the finite states of the application? Let's get back to the input problem again. In the first iteration, input was empty. So we can say that the finite state of the input is now empty. The finite state is like the different behaviors of the UI, different renders of the input that you can call them by a unique name. You can say the input is empty. Then you can say the input is invalid. Then you can say input is still invalid. And at the end you can say input is valid. We of course have to track the value of the input, and that's what we call the infinite state, but it's better for us to model it with a finite state, and you can see the benefit later on. And in order to change the rendering of it, in order for this input to be able to change, in order for this text to be able to pop up and pop out, it needs to be live, right? So we need to add an event to be able to transition between these states. So we say, if I type in the input will transition from empty to invalid if there is an invalid email. Or if I write a valid email, input goes from invalid to valid, and the only event that the input here accepts is type. You only type, and these are three finite states. The input is not going to be out of these. Or if you want to think about it as like a diagram or something, you can think of three circles, that these are the arrows that connected, and the only events are types. The good thing about thinking about states explicitly here is that you can say the system always starts from one state, and in this case, input always starts from the empty state. When you load the login form first, you can say the input is empty. So in order to now implement a way to be able to use this explicit state, you can use a union type in TypeScript. Have you used TypeScript? If you use TypeScript, you can say that there is a union type that can model the explicit state of the input. It's either empty, invalid, or valid. And you can use a nested switch case to be able to change the states. And this function with nested switch case is called the pure transition function. If you have ever used Redux, this exactly looks like the Redux reducer. It's a pure function that now instead of in Redux it changes the state. Now instead of doing that, it gives you the next state explicitly all the time. So it says it doesn't matter which state the input is in. If it gets an event that is the type of type, I can say if it's valid, the next state is valid, otherwise it's invalid. That's the whole logic of the input. Now we don't need three different properties in the object. We only need three finite states. Now the good thing here is that I want to show you this. So before this, if you wanted to show that error message at the bottom of the input, you should have said if the input is not valid and it has been validated before, there is like a logical combination of two different Boolean flags to be able to reason whether this error text needs to be shown or not. But here with explicit state, you can just say the input state is invalid. That's the only thing you need to reason about. So by moving from implicit states to explicit states, you enable your code to be able to reason based on a unique name. And that unique name is a finite state. When you think about finite state, it's so addictive. Soon you will realize that almost all the interactive elements around you in UI development are having finite states. Things like tooltips, modal, dropdowns, popover, things that pop out and pop in, fade out, fade in, and fade out, show and hide. These are always having the states of open or closed, shown or hidden, in or out. These are the finite states of all these elements. Even the button that we use all the time, its explicit states are either it's a normal state, or you're hovering it, or it's active and focused when you're pressing it, or it's disabled. This is the whole states that the button can be in. If you're making a design system, for instance, you can model the state of the button in this way, and you need to make sure that you generate the design for all of these. Also a progress bar or like a range input or a slider input or whatever people call it this year. It has a final state, whether it's in a minimum value or a maximum value or somewhere in between, like a volume slider on YouTube or something like that. It's either minimum, which is 0, or maximum, which is 100, or somewhere in between. And also you need to keep track of the infinite state too, because you need the values also as well. But not only the interactive elements, but also the side effects of using UI development, they also have finite states. Think about promises. How much have you used promises? Promises are basically a state machine. Promises are basically having 3 explicit states, and the only thing that the only event that they get are either resolve or reject. A promise always starts from pending and either resolves or rejects, either fulfills or rejects. And to prove this, I actually embedded something from the ECMAScript spec here. That's the standard behind the JavaScript implementation that says that promises are internally state machines with 3 different states. So I talked about the state machines to you without actually using the word state machines before this slide. When you look up state machines in Google, this is like the primitive way of learning something, right? We Google, we look it up. And of course, like for me, I go to Wikipedia to see, oh, what does a state machine mean? And Wikipedia in this case is not helpful. It says a state machine is a quintuple, which like I went to Wikipedia to understand what a state machine is. Now I need to look up what a quintuple is. A state machine is really challenging because it's academic and people have been using it in embedded programming or mission critical projects. It's yet unknown to web development, specifically talking UI development. But it's basically the idea is think about the finite states of the UI and think about the events that it accepts. That's the whole core idea of a state machine. But one problem with the state machines is that it's super cool. Now we like avoided all those mutual exclusivity problems and like implicit state handling, impossible states and everything. All of those are gone. But there is a practical problem here with the state machines. With the state machines, you have to think about the states. Thinking is hard. And not only that, but also everything is not as simple as a single input that has 3 states or 4 states. Sometimes the thing that you're modeling gets really complicated. It might have 100, 500, I don't know, 10,000 states. What are you going to do then? That state machine implementation is going to be even harder to understand than if and else. So in this case, we're going to talk about a solution that takes the core value of the state machines and gives you a way, it modifies it in a way that you can scale it for all the complex use cases you see in 2019 in UI development. And that's called state charts. Coming from an academic background and a paper by Derek Harrell, it basically means I have a state machine, but instead of defining 100 states, I would be able to structure them. And now I would be able to give relations between different states. I can embed children states on top of the parent state. I can say that the form is going to be submitted only if it has been validated before. So the state of submission of the form always will be embedded under a parent state, that is the validation of the input. So mutual exclusivity is gone. They also give you different ways for executing side effects, and basically side effects in the state charts and state machines are first-class citizens. So to be able to imagine these 3, it's been a lot to take, I know. So what you do is that, imagine a button, you say button.add event listener click, and then inside the callback that you pass, you say search. The search is a side effect, the click is the event. That's the normal event action that we do every day. But with finite state machine, you think about the states explicitly. And that means not only have the side effect of a search, and the event, but also tell me that in what state this event should be accepted. So always clicking on the login button will not call the login service, or always calling on the search button from now on in the state machine will not call the search service. It always does that if it's in the state that you define. So you have a search button, you have a search box, and a user starts typing something, hits the search button, and then you don't disable the button, and user is not patient, so it clicks it many times. What happens is that you're calling your API 100 times. And that's the last thing you want to happen in the UI. So what you can do is that you say that only call this search when the state is not pending. And the state chart that we talked about last was that not only get the state an event and give me the next state, but also tell me what are the effects that I need to run. It's been super boring, I know. Let's get a bit more practical. Before getting practical, let me introduce you a library. There are different implementations for just basic finite state machines in JavaScript, more than enough. But for state charts that we talked about at last, there are two implementations. One of them is called Robot, which is a lightweight version, and another one, which is like the de facto right now, is XState, which I happen to be a member of. It's based on a standard, and it gives you a way to be able to define all this logic in a JSON object, and there is a visualizer that can visualize the logic. Okay, so let's get practical. So remember the input? Now let's see what happens when you want to use the XState JSON definition, and you want to use a state charts and all this fancy stuff to model it. So here, on the right side, you can see the JSON that basically says the input starts from the initial state that is empty. Line 2. You can see that, right? Okay. So it also says that I need to keep track of the value of the input, the next line, which is the infinite state. You cannot put it in finite state. It's a value. We don't care about that. And it says whenever I receive the type event, if in all of these, if it's empty, go to the empty state. If it's valid, go to the valid state. Otherwise, it's invalid. So go to the invalid state. And regardless of which state you go, always run this action that updates the value of the input. So when user types, actually the value should update. So it runs an action to update the value, and it decides which state to go based on the condition that runs. If it's empty, empty. If it's valid, valid. Otherwise, it's always invalid. And these are the basic 3 final states that we talked about for the input before. And this is the whole logic of the input. You don't need anything else. But it doesn't make sense. It's just a JSON definition. Why would they care about it? Because now you can visualize it. So XState comes with a built-in visualizer. You basically copy-paste it. This is what I did last night. Copy-paste it into the visualizer website, and it gives you this. And now this is how you can tell the designer the input is supposed to work. The designer wouldn't understand this. You can't expect any other non-technical person to understand this, because this is like an agreement between developers, a JSON definition. But this, everyone understands. An image is worth 1,000 words. But we don't always write from scratch. Writing from scratch is sexy. It's really fun. But in the real world, we maintain. I write from scratch, I blow up, and you have to maintain. That's the real world. That's the industry. And it happens to be that not all of us work on evergreen projects. Projects grow, and legacy code happens overnight, like this. So today, everything is sexy. 2 hours after that, oh shit, everything is legacy. Writing the code is fun and easy. Maintaining is the hard part. So let's see how this state chart actually matures into the maintaining. So let's say that now we want this input to be reused in a sign-up form. So it was used in login, now it's going to be in sign-up. Have you seen the sign-up form of Google? Google, what it does is that you write an email, you say that I want to request this email. I want to make it, and Google checks for availability of this email. So what we want to do is that we want to add this availability to the same input. We want to add this feature to it. So what only business requirement we have right now is that the email should be valid before I check for the availability. If it's invalid, we shouldn't even bother calling the API. It's invalid. So what you do is that just put the logic for valid availability down in the valid state. You don't touch invalid and empty because you don't want to add any logic there. The feature is going to be only added down the valid state. And this is the structure I was talking about that a state chart gives you. So instead of writing if email is valid, if input is invalid, do this, instead of doing that, you embed it with a JSON object under valid state. So basically say, if input is valid, initially you're checking for availability. You invoke the checking service, which is a promise, which is a fetch. And If check says that it's available, you transition to available, say that input is available. Otherwise, you say it's not available. Even the JSON is readable. And you can visualize it. Now you can see that the previous input, that was pretty easy. There is a checking here now. And it's always undervalued. So next iteration, project manager comes and says, oh, you know what? You're calling the API all the time. They're exceeding the rate limit. Now you need to debounce it. So how debouncing works is that a good thing about state charts is that they have time-based enhancement built into them, because it treats it as a normal event that has a delay. That's the whole modeling for debouncing, throttling, delaying, or there are like different other several time-based enhancements, but let's not get into that. So to debounce, you remember that we said it starts from checking. Instead of going to checking to call the API, you go to debouncing, and in debouncing, just wait for a debounce delay. That's the whole debouncing logic. 3 lines. Usually debouncing is very critical, and not many people understand. And now the debouncing logic comes here. Now everyone sees that it starts from debouncing, and after a debounce delay, which is 300 milliseconds or whatever, it starts checking. So again, the product owner or the project manager bothers you again and says that, hey, you forgot to cancel the network request. You not only have to debounce, but you also have to cancel the network request that was on the fly. So instead of doing that, you add 2 lines of code. You say, when I intervalid, initial fetch controller, which uses like abort controller or something, get the signal, pass it to the fetch, and whenever I'm going out, which means the user has typed something new, just cancel it. That's it. That's the whole thing. Network cancellation, which is super fancy and like complex for most of the tutorials you find online, it's just 2 lines of code in state charts. And now it just labels them to here. But you might wonder, it was only JSON. It was abstract. It was declarative. Where the hell does this implementation go? Where do I do the actual abort controller and stuff like that? So let me tell you something. XSA tells you to define something as JSON. There is a machine factory that you can import from XSA library. You can pass it the JSON, and it makes you a state chart object. And then you can initialize this state chart object with whatever config you want when you're using it, not when you're defining it. The definition of the logic is still abstract. You can just put it everywhere you want, but you can define it whenever you're using it. You can say, these are the actions. You know what? I said I have an update value action, so this is how it works. I said that there is a check service for checking the availability of the input, which is supposed to be a promise. This is the implementation. These are the guards for being empty and valid, and even the delay for the debounce can be abstract. And all of these are called entities, and every entity in XSA notation gets access to the current context, which was the value of the input in this case, and the input event that's coming. So you have full control on everything, and you can define all the logic you want. But this implementation detail has no way to get into the abstract definition. The JSON is abstract all the time. It was very static. It was a basic form and input. Even though it was really basic, you've seen that adding cancellation and debouncing and checking for availability of the input, how much it increased the complexity of a single input. The input can be that complex. We just underestimate the complexity of the UI we build all the time. But let's see these state charts. How do they mature with interactivity? What if I want to drag a box in a container and I want to model it in a state chart? So how would you think about that final state in case of this interactivity? So in case of an interactive box, you can say that the box is released initially. You just release it, it's there. Then I press the mouse so I can send a grab event. I say that I grab the box. And it transitions to work, please. Transition, work. Yeah, it worked. It went to the grab state now. So there is a box. You press the mouse, the left click, it goes to the grab state. And after that, you say that I can start moving it. And whenever, as soon as I start moving the box, change the state to dragging. And in dragging, regardless of how much I'm moving it, keep it in dragging, because I want to real time move it all the time. So I keep it in dragging the state, and No? Yeah. And whenever I release it, just get back to the release state. And that's where, like, you know, a mouse up. You release the left click of the mouse. So the JSON and the boxes that we saw. So we say in the JSON definition, the box is initially released. In release state, you can only send grab events, and when you grab it, it goes to grab state. And as soon as you enter the grab state, you save the current position of the mouse inside the small box for calculations. You save the current box position inside the container, again for calculation and moving. You prepare the box size, meaning that you can change the size of the position into absolute, so you can actually move it by tweaking the top and left. And you can actually move it, and moving can be just tweaking the actual style object. And on the next step, you can say that if it's dragging, as long as I'm dragging, save the current box position inside the container, save it and update it all the time, and move it. And only when I get released, when the mouse is up, go back to release and forget about everything. That's the whole model of an interactive dragging box in the container. And if you want to visualize it, there's a built-in visualizer. You can see that there are 3 events, and there are 3 states, and so on and so forth. And how you can connect it to the actual event handlers is that basically that's it. You don't do anything. You just get the events, proxy them to the state chart. A state chart will take care of it. And when I say take care of it, it's just that JSON object. So when mouse is down, start pressing, just say that I grabbed. When mouse is moving, just say I'm moving. And when mouse is up, just say I'm releasing. That's it. So I want you to be able to compare the old implementation, which is handling it imperatively in all the event handlers, with if and else and 3 event handlers, and on the right side is just a JSON object. You can judge on yourself, this is your call, which one is more readable. But along all this stuff that I said, all these benefits, I have a very cool demo for you in additional benefits of using state chart. It's a topic that there is a lot more depth to it. There is automatically generating tests. There is like being able to visualize the path that the user can take in your application. There are like so many fancy stuff you can do with the state charts. But today, the only thing I want you to do is to think about the states explicitly. Just remove all those objects you have and start thinking about inputs, forms, tooltips, and stuff explicitly. You remember the dragging box JSON definition, right? It reads like English. Like basically whatever I read for you, it can be released. When it's released, it can be grabbed and stuff like that. It's basically reading like English. It's human readable. And to prove that it works, I'm going to show you a demo. This is using the natural language processing to interpret the JSON definition here. I wrote it last night before going to sleep. So it uses natural language processing to conjugate verbs and understand what's the human way of transforming this, transforming this JSON definition to a human readable sentence. And then it tries to read it for you, and it uses the web speech API. So this is an embed from JS Fito. I'm not mocking it. This is an embed. I can give you the link. So I'm just clicking it here. Listen.
Dragging box is released at first. When it's released, it can only be grabbed. As soon as it's grabbed, we save box position in box, save box position in container, prepare box styles, and move box. When it's grabbed, it can only be moved. As soon as it's dragging, we save box position in container and move box. As long as it's moving, we keep it in dragging, which means continuously save box position in container and move box.
And your code can talk from now. Along these benefits, there are also another benefits too. Gods of demo. Yeah. All right. So I'm not good at drawing. I'm sorry. So this is the best I can come up with. Along all those benefits that we saw, all those fancy stuff, we could make the code talk. There are other benefits too. So when you start defining the logic in a JSON object, as long as you keep it serializable, you keep it abstract and declarative, and you don't put implementation detail in it, you can generate a directed graph, which is a dependency graph between different states of your application, and you can basically see how the application can live like a story. And based on this directed graph, you can visualize, generate tests. Actually, the XSH visualizer works based on the directed graph under the hood. You can showcase all the state paths. Imagine you use the state charts for modeling Amazon e-commerce. You can say that there are like 1,502 ways to get from the home page to payment success. Because the state chart will give you that exact number. It will tell you these are all the possible paths. These paths can be used by QA. So your QA department in the product development doesn't need to do a smoke testing and randomly dispatching from now on. It can just take a look at all those paths in the visualizer, try to see the dead end in the visualizer, and then try to reproduce it. So it saves a lot of time and effort. Besides that, it's very good for cross-competence teams. Teams are not always including only JavaScript developers. Sometimes you have Android, iOS, and web developers, and like other stacks too. And it's quite hard for us as different developers with different backgrounds to talk about certain logic or feature without getting into the implementation detail. Next time, when you're trying to define a side effect, try not to talk about promises. It's quite hard. But besides all these developers from different stacks, we also have product owners, salespeople, marketing people. These are all the people that are going to be a part of this product feature, but they just can't talk about the implementation detail. They don't know anything about development. So this is a very good way to communicate between them. So instead of writing the code and getting the feature done, go on and draw the visualizer, like write the JSON file, let it visualize, and then talk about the same feature. It's very good for onboarding. Next time you want to onboard someone, instead of pushing them like 300 pages of documentation written in YAML or whatever, just give them some visualization of the architecture. They will understand it. They're smart. And this is actually a live pull request from the Gatsby repository. So one of our team members, he went there to update XSH version. Gatsby is using XSH under the hood. So it went there to update XSH version from 3 to 4. He ended up adding some other features too. And in order to tell Gatsby people how this works, he actually used the visualizer. So we dubbed Food Visualizer too. It's a very great way to communicate the logic in pull requests. So this is something you can use from next Monday. And talking about the porting of logic, you've seen that we've always dealt with abstract declarative JSON. I never talked about how moving box works. Technically I talked about it, but I didn't write it or show you in the code. It's because I communicated the logic with you. You understood, you followed, but we didn't get into implementation together. So this proves it that you can port that JSON into different platforms and write the implementation config for the state chart when you're running it on different platforms. The JSON will be the same. When you're updating a feature, you can update the JSON, which updates it for everyone on different stacks. And you just have to tweak the implementation for yourself. So I hope next time someone asks you, how hard is it? Is it just adding an if case? Or is if and else, right? You say, okay, let's draw this state chart for it and see how it's complex. It gets complex. So to have a really quick recap, we learned that there is actually a modeling layer, we just don't use it. We saw that we can code in a way that our solution gets even more complex than the problem itself. Complex problems require complex solutions. Your best shot is to make them equal. That's it. Another thing is that we've seen explicit and implicit states, and we've seen finite and infinite states, and we've also seen that state charts are a very good way to be able to model complex application logic. So they also make impossible states impossible truly. You don't have to write tests or guards to avoid them. They also are a very good they're basically framework agnostic. They are technically language agnostic too. I had a demo in one of my conference talks that I implemented a video player volume changer in Erlang, Vue, React Native, and React in Terminal. So it worked on Terminal too. You have to model the code in a way that you don't know how you render it, because the logic to mostly is not dependent on the implementation. A state chart can be used for component level state. You can bundle a definition with each component. They can also be used for app level state, but talking about that will get us into actor model and architecture like that. We don't have time for that. They not only avoid impossible states, they also avoid mutual exclusivity problems. So your forms are not going to be submitted if they're not valid before. They are very good for knowledge sharing and stuff like that. So as I said before, don't get into X state, anything, visualizing anything like that. You want to use it, cool. Go on, check the official docs and everything. But the only thing I want you to take away from this talk is to start thinking about the states explicitly. Just think in states, and instead of thinking in transitions and side effects. And I don't want your code to bully you from now on. It's a matter of taming the control. Either you are in the control or the code. If you don't model the code, the behavior will shape implicitly around the code. So be aware of that. Thank you very much.